Hello everyone, so we're back to some volumes of revolution reborn. So what happens is that my previous calculus teacher, Mr. Lassa from Secaucus High School, challenged me to find the volume of revolution when, let's say, a line like y equals x squared is revolved about another curve like the square root of x, which is also its inverse, right? Because if we draw a line that is y equals x, it's going to go right through the middle of each of the two curves, right? So that means it's the inverse, because if we plug this into a composition of functions, we're going to get the value of this functions, which is going to be x. But that's just a very curious observation, but we don't need that for this problem. So before we learn how to revolve volumes, revolve curves about other lines that are parallel to the x and the y axis, and also slanted axis, which is a little bit more difficult, but it's definitely possible to do. But now, my teacher was wondering, well, how can we revolve, one curve over another curve, and then find the volume generated when you rotate that area, right? When you rotate this area that is enclosed by the curves about the same curve. That's hell of a question, right? It's not very easy. So it took me like 2 weeks to come up with some sort of even understand it, or even being able to visualize it, because it's not very easy to visualize it, right? So it took me a while to at least see what it really means. And I think it was yesterday. This guy Dustin Kendall from Facebook, pretty much came up with a really cool method on how to solve this. So that's why I want to share this method with you guys today. So basically, what's going to happen here is we want to find the radius, right? We want to use the disk method. And so we need to find the radius in order to add up all the disks, from here to here. But in order to do that, we have to define what our axis of rotation really is, right? In regular volumes of revolution problems, for example, in the original problem that I have done before, which is rotating y equals x about the line rotating x squared about the line y equals x, basically the radius is always perpendicular to the axis of rotation. So that's very key to the problem. If the radius is not perpendicular to the axis of rotation, then we're going to have to use a different method, right? It's not going to be the disk method. Now in this case, if you think about it, this is going to be the axis of rotation over here, the square root of x, right? And in order to find, the radius, we need to, find lines perpendicular to each tangent on this curve. So essentially we need to find the derivative of the square root of x. So suppose that you have a tangent over here, right? And so you need to find the perpendicular distance that connects to another point over here. And that's going to be your radius. But how are we going to find that? Right, that's really complicated. Some people might say, well, you could use the distance formula, right? Between the 2 points, but then you're not going to have just 2 points. You're going to have an infinite amount of points, which means you're going to have an infinite amount of axis of rotation. You're not going to have just one axis of rotation. That's pretty trivial. Here you're dealing with many axes of rotation, which is essentially the derivative of the top curve. But now I'm going to show you a very cool method that Dustin Kendall came up with, and I revised, all of his steps, and it's just pretty cool. So I'm going to show it to you guys. So essentially, what he said, well, let's assign this tangent, a vector. So let's call this vector s, right? So ds. Let's call this vector ds, and it doesn't really matter how large this vector is. The magnitude doesn't matter. And then let's call the perpendicular vector to it that connects to the point in the lower curve, and that is perpendicular to ds, and let's call it r. All right, for radius. Now, here is something to observe. If we don't care about the magnitude of ds, then we can say that it is an infinitesimally small vector. So we can find the components of it, right? So right here we have dy, and right here we have dx. So we can already write that in component form, right? So we can do ds is equal to dx x hat plus dy y hat. Now, I'm writing this in differential form, but in reality, this is just dx over dx, and then this is dy over dx, so essentially the derivative. Now, dx over dx is just equal to 1, so we can get rid of that, and so it's essentially just 1. Okay, now we're going to find the components of this vector r. In order to do that, we need to define some points. We need to define the coordinates, okay, the x values of this point over here. So we're going to go all the way down here, and we're going to define it as x1. And for this point, we're going to do the same. So this is going to be x2. And for instance, the values of the function are respective with each curve, okay? So we're going to go ahead and define the components of this vector. So we have the x component and the y component. So r is going to be, the x component is going to be this, okay, this minus this, right? So this x coordinate minus this x coordinate. So x2 minus x1, x hat. And then the y component is going to be the value of the function over here, which is going to be x2 squared minus the value of the function over here, which is going to be square root of x1, y hat. Very nice. We defined two vector functions that are going to help us solve this problem now. Now here's what is going to happen. We already have a function for the vector, right? And we need to add up all the vectors squared times pi from here to here along the curve. We're not integrating along x, right? Because now we're integrating in terms of each tangent. So we're going to have to do something pretty trippy here. I apologize, I'm a little sick, so bear with me. Now, this is what we're going to do now. We want to find, okay, this function in terms of only one variable. Okay, we're going to find it in terms of x1, so that means we want to know what x2 is in terms of x1 and substitute it in these two values over here. Now, here's something to note. Since these two vectors are perpendicular to each other, we know that the dot product of these two vectors, so ds dot r, is always going to be, right, the magnitude of ds times the magnitude of r times the cosine of the angle between them. And the angle between them is 90. Cosine of 90 is 0. So essentially, that's equal to 0. So we can go ahead and calculate the dot product of these two vectors. So that's just going to give us, okay, r dot ds, right, is going to give us that times this. So it's going to be x2 minus x1. And that's going to give us plus x2 squared minus the square root of x1. All of that multiplied by the derivative of the top curve. Now the derivative of the square root of x is 1 over 2 square root of x1. All of that is equal to 0. And right here we have, okay, an equation that's in terms of two variables, x1 and x2. So we want to find that in terms of x1, right? So we can plug that x2 in here and then find everything in terms of x1 to make things easier. Now over here we can multiply by 2 times the square root of x1 to get rid of that fraction. So we're going to have x2 times, right, 2x2 times the square root of x1 minus x to the 1 times x to the 1 half is x to the 3 halves. So that's going to be times minus 2x1 to the 3 halves. And then we're going to have plus x2 squared minus the square root of x1 equals to 0. Now, note that for this problem, for this equation over here, we can observe that there is a quadratic function in terms of x2. So if we underline all the x2's in here, we find that if we treat x1 as a constant, right, so we're going to treat x1 as a constant, we can certainly use the quadratic formula to find x2 in terms of x1. So we're going to go ahead and do that. So x2 is essentially negative of b. Now b in this case is going to be 2 times x2, right? I'm sorry, 2 times the square root of x1 because x2 is the variable we're solving for. So negative 2 times the square root of x1, right? So that's going to give us minus, plus or minus, right? The square root of b squared. So that's going to be 2 times the square root of x1 squared, right? Minus 4 times ac. So that's going to be minus 4 times. Now the a in here is going to be 1, and c is going to be this entire thing over here. Okay, so keep in mind. So that's going to be 4 times negative 2x1 to the 3 halves, and then minus the square root of x1. All of that divided by 2 times 8, so 2 times 1. Okay? Very cool way to use the quadratic formula. You know, actually applying things that we learn like in high school or college is probably the hardest part. And this is probably one of the coolest ways you can use the quadratic formula to solve for a variable in terms of another variable. Very clever, very clever. Now, let's go ahead and substitute and then simplify this in here. So you have negative 2 divided by 2 is just 1, right? So that's going to give us negative root x1. Now for this plus or minus, we have to make some restrictions. We're solving for something that's greater than 0, right? So the values of x1, the values of x2 have to be greater than 0, right? So we have to say that x2 is greater than or equal to 0, right? And we can also say the same for x1. So x1 has to be greater than or equal to 0 because we're integrating on the open interval, right? So from here to here. Since it's differentiable and it's also continuous on the open interval. On the open interval. Now, we're going to consider only the positive values. So we're going to have plus the square root of 4 times x1 plus, this is going to be 4 times 2 is 8, right? So that's going to be 8x1 to the 3 halves plus 4 root x1. And then all of that divided by 2, right? Now, if we divide that by 2, it's basically the same thing as bringing that 2 inside of the radical as a 4. So we can divide all of that by 4 to make things a little bit more simplified. So we got x2 is equal to negative the square root of x1 plus the square root of x1 plus 2x3 halves plus root x1. And so this is basically, okay, the value of x2. And finally, we can substitute x2 into our value of, and our vector valued function of the radius, right? That we're going to integrate in our integral later on. So let's go ahead and do that. So that was a very clever method, right? Taking the dot product of both vectors and figuring out, okay, the value of this. So now let's see. Oh, I erased this by accident. All right, now let's substitute that in there. So we have that the radius vector function is going to be negative square root of x1, right, plus the square root of x1 plus 2x1 3 halves plus the square root of x1. And then we have minus x1. All right, x hat. And that's going to be plus that square, the entire thing squared, so negative x1 square root of x1 plus the square root of x1 plus 2x3 halves plus root x1 squared, right? All of this inside squared. And then, of course, don't forget to subtract minus square root of x1. All of that y hat. Okay. Now, this is essentially, okay, saying that x1, right, is equal to x. Okay, so we're just going to say that x1 is equal to x for this case, since we're only integrating in terms of the curve. So I'm going to show you what I mean by that in a second. Now we found the the vector value function for the radius, and of course we have to find the magnitude of the vector. But first, let's see what we're looking for, right? So we're looking for an integral. So the volume of the solid generated when we revolve x squared about the square root of x should be pi, right, times the integral from 0 to 1 of the vector value function, the magnitude of the vector value function, so the magnitude of r, right, squared, times ds. Now, see, this is the weird part over here, but it's very clever. We're integrating along the curve. We're no longer integrating about a straight axis. We're integrated about an infinite amount of straight axis. So that's the crazy part about it. Okay? So first we have to find ds in terms of dx, and then we can find the magnitude of the vector valued function squared, right? That's pretty useful to know that when you find the magnitude of a vector, you have to take the square root of both. If you have two terms, two dimensions squared, you can get rid of the square root, right? So let's see what happens with that. So let's find the magnitude of the vector squared first. So we can say that the magnitude of the vector, okay, squared is going to be equal to the square root of, okay, negative the square root of x. Now we said that x1 is equal to x, right? Plus square root of x1 plus 2x, 2x 3 halves plus root x, okay, minus x. All of that squared, because that's going to be the x component, and then we're going to add the y components squared. So negative square root of x plus square root of x plus 2, x 3 halves, pretty much the same thing, plus root x minus root x1. All of that squared, and this inside is squared as well. Okay, that's a pretty long thing. And now that's the magnitude only, right? Now we have to square the magnitude, right? So we're going to square that. And well, once we do that, as you can see, we get rid of the radical sign over here. So let's go ahead and find ds now. We have to find ds. We know from the original equation over here that ds is equal to dx x hat plus dy y hat. So if we use the Pythagorean theorem for that, we can say that ds squared, right? ds squared is equal to dx squared plus dy squared. So that is the same as saying that ds is equal to the square root of dx squared plus dy squared. All right, and remember that dy is essentially the derivative of the top curve. So let's go ahead and take the derivative of the top curve. So since y is equal to root x, dy is 1 over 2 root x dx. So we know that ds is equal to, okay, the square root of dx squared plus 1 over 4x dx squared. Now we can factor out a dx squared, right? And as you can see, that's going to come out as 1 dx. So let me just write that. I have no more space. Let me erase the top part of this. All right, so we can say that ds is equal to the square root of, right? If we use some common denominator skills over here, we have 4x plus 1 over 4x. All of that times dx. That's going to be ds, okay? Now, finally, we can put everything together in our integral. So we can say that, okay, once and for all, let me make more space because that's not going to fit in there. Okay, once and for all, okay, the volume of revolution, and I'm not going to solve the integral because I don't have time for that, it's too much. So it is left to you as a trivial proof, as an exercise for the viewer. So we're going to go ahead and take the integral, okay, pi times the integral from 0 to 1, okay, of the magnitude of the vector squared. So we found the magnitude of the vector squared. That's going to be this entire messy function over here. So let's see what happens. So minus the square root of x plus square root of x plus 2 x 3/2 plus root x, okay, and then minus x, all of that squared, and we're going to add root x, negative root x, plus the square root of x plus 2 x 3/2 plus root x. This is squared, right? And then we're going to subtract root of x and all of that squared again. ds, right? And of course, ds is that, so we can just multiply by that. I don't know if you can see this. So let me actually make more space so you can see the actual final integral, final answer. So the volume, okay, of the solid generated is going to be pi integral from 0 to 1 negative root x plus root x plus 2x to the 3/2 plus the square root of x, right, minus x, all of that squared, and then we're going to add, okay, negative the square root of x plus the square root of x plus 2 times x to the 3/2 plus the square root of x minus the square root of x. This inside is squared, and then everything together is squared again, times ds. ds in this case is the square root of 4x plus 1, right, divided by 4x dx. So right over here, ladies and gentlemen, is the volume of the solid generated when the function y equals x squared, the curve y equals x squared, is revolved about the curve, the square root of x. And when you plug that into decimals or Wolfram alpha, you're going to get something about, you're going to get about 0.19 cubic units. And you know, that kind of makes sense. If you remember from my previous videos, I posted something about the volume of revolution, about the slanted line of x squared, right, about y equals x. It was about like 0.07 something, right? Now the ratio of that is about 2. It's about 2.5 times. So the ratio of this volume of revolution over this is about 2.5 times greater. So this is 2.5 times greater, about 2.5 times greater than that. And that kind of makes sense, since you're revolving like twice as much area. But in this case, we're not revolving about any straight line. We're revolving it about square root of x, which is not a straight line. But yeah, it's pretty cool. So I hope you like this video. This is it for now. I believe there is many other ways to solve this problem, but this is probably the only way I know as of now. I'm thinking about doing another video of some other examples using this method, which is due to Dustin Kendall, very, very smart person. So I'll see you soon. Please subscribe to my channel, share this on your social media, and comment, like. I hope you like this. All right. Have a good night. Gotta go to class.